All right, so last time we were looking at electromagnets a little bit and electromagnetism, where we could take coils of wire with current going through them, and especially when you put a piece of metal into them, they can be used to create insanely strong magnetic fields. And especially if we take a piece of iron inside and put them there, that iron then becomes magnetized and can actually have that magnetic field travel to different places or different parts of the setup in order for you to actually use it. So we sort of had stuff like this. Remember, this is called a solenoid. So this is a solenoid. It's like a tube of wires. And then if we have like a piece of iron inside of it, something like this, there's my piece of iron, nice and long. Like, there we go, nice piece of iron. Okay, and let's say let's draw our current coming down this side. And then if you use your right hand rule, remember to make your fingers the current. So using your right hand, your thumb should be pointing towards the right and your fingers should be wrapping down on this side and your thumb is pointing to the right. So inside of here, the magnetic field would be going towards the right, which means it's going to come out this side and wrap around like this. But the thing is, since the iron side, this is an iron core solenoid, the iron would then continue that magnetic field and it would come out here, and that's where it would actually loop around and come all the way around. So this would become the north end and this would become the south end. But then you can take that piece of iron and you can bend it any way you want to put the north and south pole wherever you need to put them in order to actually apply them to different things. So we use things like solenoids and other types of coils of wire to actually create the magnetic fields. And then we can use things like iron to actually both contain and move the magnetic field to different places that you might actually want to put it. And we use this for tons of different things. And this is basically the idea behind what we call electromagnets. And of course, one of the oldest tricks there is to take an old iron nail or a bolt, wrap some wires around it, hook up a 9-volt to it, and it'll magnetize the nail or the bolt, whatever you're using. It turns into a pretty strong magnet. So this is the idea behind electromagnets and electromagnetism, which is used for tons of different stuff. Okay, so for example, something like this, the crane. Okay, this is a crane in something like in a scrapyard or something like that, and that's basically a giant electromagnet. And the nice thing about electromagnets is you can turn them on and off, and they have insanely powerful magnetic fields. You turn them on, you turn them off, and you can turn the field on off instantly pretty much. It works really, really well. So they turn on, pick up iron, and then move it across, and then turn it off, and it lets the iron go. And there's thing is you can actually use them for sorting. If you got like a whole bunch of scrap metal on a conveyor belt, they'll put electromagnets on there, and when things like aluminum and things that are not magnetic go over it, nothing happens to them, but the magnetic stuff will get stuck to the magnet, and then you can just move it somewhere else and turn it off and let it go. You can also use it in speakers. I mean, that's how speakers work. Speakers usually are a combination of two magnets inside of them. And when the signal from the whatever sound source you're looking at, whenever the signal goes in there, it interacts with the electromagnet. And then the permanent magnet and the electromagnet inside attract and repel. They interact when the current and the signal goes in, which then moves the actual diaphragm of the speaker, which actually creates the sound. So all speakers use electromagnets like this in order to make them actually work. Microphones are exactly the same thing, except sort of thrown in reverse. We've got bells, like good old like fire bells and school bells and that type of stuff. They use electromagnets. When the current goes in, it turns on that little tiny magnet that's in here, and it attracts the little hammer, and the hammer then slams against the bell, which makes it ring. But when it does that, it actually breaks the circuit, which turns the electromagnet off, which then allows the little hammer thing to spring back, because it's usually attached to a spring, which then reconnects the electricity, which turns the electromagnet back on, which then attracts the hammer and slams it into the bell, which then breaks this contact, it breaks the circuit, which turns it off. And this is what happens. It goes back and forth, and these bells go on and off incredibly fast, and that's just how fast and quickly you can actually change or turn off an electromagnetic field. Last picture here is another common one. It's like one of these electric magnetic door things, like in a school or a business, like a fire door. So when the fire alarm goes off, the electricity is cut off to the circuit. It lets the electromagnetic go, and then the door is just automatically closed because the magnet's been turned off that was holding them in place. Okay, MRIs. MRIs are gigantic electromagnets, and they have coils of wire all over the place, and they send out magnetic fields, and that's how MRI imaging works, because it stands for magnetic resonance imaging. And you're basically just lying inside of a giant solenoid is what you're doing, and it takes magnetic images, which is really kind of cool. Magnetic levitating trains, like super smooth, super fast trains. They'll use solenoids and electromagnets to get them off the track to reduce friction and noise and all that kind of stuff, and they just run super smooth. Some of the same ideas are applied to this, which is actually for a roller coaster, where they'll use electromagnets to actually boost and fire off roller coasters that would sort of like the roller coasters that shoot off at the beginning. Really, really cool, and just really strong magnetic fields can be used for that. This is sort of like a section of that where you can see like how the rails work, and there's sort of magnets and electromagnets, and then you have they sort of like on either side of a rail to give it stability and stuff like that. It's really kind of cool. This is a rail gun actually, where electromagnets can be used to actually shoot projectiles, and you can sort of see you got the current going around it, and you sort of see the magnetic fields going around, and you sort of have that projectile thing that sort of slides across the rails, and as long as it's in contact with the rails, there's the current going through there, there's magnetic fields being produced, and it's the interaction and repulsion of those magnetic fields that actually caused the projectile to actually fire out. And there's like no gunpowder, no noise, no nothing, so it's kind of quiet and stuff like that. So it's kind of cool. That's what's called a railgun. So electromagnets are used for tons of different stuff. These are kind of specialized type things, but even common everyday things everywhere, from bells and speakers and microphones and fire doors, they are everywhere. So electromagnets are really, really, really handy and used for tons of different stuff. So good old electromagnets, that's what we're talking about. They're very, very quick for on and off, which makes them really, really handy to have. You can have them in lots of different sizes, as well as lots of different strengths. They can be really, really small, like in the headphones that you listen to, or they can be really, really big, like on the crane. They're quick on off. There's lots of sizes. There's lots of strengths. They're used for tons of different things. Really, really, really handy. Okay, so electromagnets are all over the place if you know where to start looking for them. And in grade 12, we'll expand on this with electromagnetic induction, which is also connected to this type of stuff as well. Now, one other thing that this leads into, and if we're in regular classes, we'd spend some more time on this, but this is sort of the quicker version, the online version while you guys are learning at home. Suppose we had a wire like this, and we had a current going through it, so current something like this. It would produce a magnetic field, and using a right-hand rule number 1, the magnetic field would actually come around like this and something like that around the wire. Now, what if you took that wire with a magnetic field and it was already in a larger magnetic field? Okay, so this, we get something else going on. If you take a wire with a magnetic field, that wire's magnetic field actually interacts with an external, fix that up, with an external magnetic field. And that would be this one out here. There's my external magnetic field. And when two magnetic fields interact, you actually get forces, and there'll actually be a force on that wire. And again, we don't have time to do this, but in class we look at this a little more. You can actually calculate the force on that wire. It's actually the product of the strength of the magnetic field that's outside of the wire, multiplied by the current going through the wire, and then you multiply by how long the wire is, as well as sine of the angle, because you want the wire to be actually cutting the field. and you can calculate how strong the force would be on that wire. And again, if we were learning in the lab, we'd be working with this a little more, but you guys learning from home, so I just want to make sure you actually have seen it at least. Now, this is the idea behind the forces that actually create electric motors. So this is how electromagnetism and electromagnetic induction, that type of stuff, we'll do this more in grade 12 as well. This creates electric motors, because if you've ever cracked open an electric motor before, there's basically two things. There's magnets and loops of wire. And sometimes there's just two sets of loops of wire. One set of loops of wire is used to make magnetic fields. The other one is about feeling the forces. So when you get these two things interacting, you have a force created, and then you take hundreds or thousands of pieces of wire inside a magnetic field, and you can create insanely strong electric motors, and that's how they work. So when you guys use electric motors, well, what are you guys actually doing? Well, there's a magnetic field inside of the motor. When you turn on the motor, you are putting current through it, and the more current you put in through it, the faster it goes. So if you use like an electric drill, and the more you pull the trigger, the faster it goes. Well, that's why, because you're putting more current in, you get more force, and it works better, it goes faster. And then there's also the length of the wire. The longer the wire is, the more interaction you have between the wire and the field, and you get more force of it. And you also want it to be, you want the two to be perpendicular. And we'll look at that a little more in grade 12. But that's how you can calculate the force. And that's sort of what this eventually leads into. Aside from creating electromagnets and making really, really strong magnets, you can actually start calculating forces with this type of thing, which then leads to electric motors and electric switches and a bunch of other stuff where magnets and currents work together to create electric or magnetic attraction or repulsion to get forces involved to do different things. Okay, so again, we can't do as much in magnetic fields as we do in electric fields, especially, or even gravity, but especially in electric fields. You can do a lot more stuff with magnetism in grade 12, and there's some really, really cool things that magnetic fields can do, but we can look at that a little more next year. For you guys, it's more about the nature of the magnetic fields, the idea behind domains, and how to find and draw magnetic fields around magnets, as well as wires, coils of wires, solenoids, stuff like that. And then just a little brief introduction here, especially for next year, about how this interaction can then result in forces.